All right, so we had one last topic to cover in chapter 4B, which we'll do right now, and then we'll move into 4B. So anyway, what is this all about? So we're going to be looking at global extrema over a specified interval rather than over the entire function. Okay, now by doing this, it introduces the possibility that the extrema occur at the actual endpoints of this interval. So in other words, if we had something like this, and we specify that let's say we're only interested in this interval from I don't know, 2 to 4. Then this is clearly a minimum within that interval, but one of these endpoints could be the maximum within that interval. So in other words, even though clearly neither of these points is the maximum for the entire function, if we're only interested in the area between 2 and 4, then one of these two endpoints could actually end up being a maximum or a minimum. Now, when would you ever run into this, by the way? In a lot of applied disciplines, we only have the possibility of positive values for x and y. So we may have some kind of a function where we have, let's say, something like this going on. And actually, let me try that again. So if we're only restricted to the first quadrant, that means no matter what happens out here, this, it appears the way I've drawn it to be a global minimum. Because even though there's parts of this function, like over here, for example, that are smaller than this, we're only concerned with values from 0 up to infinity, because this is some application, like maybe this is a cost function, for example, in economics, where you cannot have a negative number of units of the good that we're producing. So from 0 up to infinity, this is the smallest value that we're going to find. So we can think of this as a global minimum within the interval from 0 up to infinity. Okay, so that's really why this is important, because we know perfectly well that we may have a smaller point out here somewhere, but that is irrelevant when we're dealing with a situation where we can only have non-negative x's and y's. Okay, so anyway, here's just a quick review. I just wanted to throw this up there one more time. We're kind of beating this to death, but the word minimum has a plural of minima. The word maximum has a plural of maxima. The word extremum refers to either a maximum or a minimum, and the plural of extremum is extrema. All right, so a couple of graphs to review what we've been doing. The one on the left, you can see it has a local maximum and a local minimum. That simply means this local minimum, maximum is not necessarily the largest point in the entire function, but within this area, which is sometimes called a neighborhood, it is indeed the largest value of the function. So we'll call it a local maximum. And then over here within this neighborhood, this is the smallest value and we'll call that a local minimum. Now, what often can happen is there can be multiple local maxima and minima, and then we have to find the largest of them all to determine the global maximum. And then the smallest of all the local minima is called the global minimum. On the right, you can see two functions where we do, in fact, have a global maximum and a global minimum. So anyway, so now we're going to consider the cases where the interval of interest to us is not the entire real number line. So here, for example, we have the 2 points A and B. And so we're only concerned with the behavior of the function in this range. And so what we're going to do is find if there's any global extrema within this interval. And now, if you notice, they're telling us to look for the critical points in the interior. And remember, we find these where f prime of x equals 0. But we also have to check the two so-called endpoints. These are called endpoints now. Just in case they happen to be the extrema that we're looking for. But the basic logic never changes. I mean, we're still trying to find the first derivative and set it equal to 0. And by the way, and here you can have multiple results. So again, the whole idea here is the largest of the values that we find is the global maximum over that interval. And then you can have over the interval AB, if there's a smallest value, it's called the global minimum. All right, so let's start with a simple case of a parabola, which is facing down. You can tell because this coefficient is negative. But the interval that we're looking at is only 1 to 3. For some reason, we're only concerned about the interval from 1 to 3. It could be that this is the function that describes profits for producing anywhere from 1 to 3 units of this product. For some reason, we cannot produce more than 3, let's say. So here's what the function looks like. And visually, you can see it's pretty obvious that there's a global maximum right here. But there could, well, we have to consider the 2 points, which would be, let's say, here. And let's say here. This is where we have the 2 endpoints of this interval. And we have to test them both as well to see if they might actually be extrema. Okay, so this one we know because we can see for ourselves the tangent line is flat. The tangent line has a slope of 0. Or in other words, f prime of x, whatever that point is. Let's say this is point x star. The f prime of x star is 0. That's obvious. And of course, we're going to have to find it, but we also want to test the function at these other 2 endpoints. All right, so first we have to take the derivative of this function. What we're doing here is we're actually identifying the 2 endpoints. So there's when x is 1, by plugging that into the original function, that gives us a value y is 0. Okay, so let's label that here. This is the point 1 comma 0. And what about the other one? When x is 3, y is negative 2. And so that's what we have here, 3 comma negative 2. So what about this point? That one we can find by taking the first derivative of this function and setting it equal to 0. Okay, so based on the power rule, we have, remember this one is, can be thought of as kx to the negative 1. The k here is actually negative 1. And so the first derivative of that term is nk x to the n minus 1. So I have 2 times negative 1 times x to the 2 minus 1. That's negative 2x. And then for the 3x, there's an implicit 1 here, so you'll have 1 times 3 times x to the 1 minus 1. or 3x to the 0, or just 3. So in other words, the first derivative of this function is negative 2x plus 3. And what we want to know is, where does this equal 0? Okay, because that will give us one of our extrema. So we said negative 2x plus 3 equal to 0. Subtract 3 from both sides, divide out both sides by negative 2, and this is the result. So we call this a critical point, as you recall. Critical value. Now, what about the y-coordinate for this point? That's easy to find. We'll do that in the next slide. We're looking for f of 3 halves, so we plug this in, and you can see that we ultimately end up with 1/4. So the point 3 halves, 1/4, is what we call a critical point. Okay, so the x-coordinate is the critical value. The entire point is the critical point. And we know that this is a candidate for either being a global maximum or a global minimum. So if we go back to the graph, it should be clear that it is a maximum. But how do we prove this algebraically? All right, there's a couple of options. So the points 1, 0, 3 halves, 1/4, and this one was 3, -2. All right, so the key detail here is this. F prime of x, we discovered, is -2x plus 3. So f prime of 3 halves is 0, as we expect. Okay, that's how we discovered that this is an extrema in the first place. Now, what we can do is try a value of x that's slightly to the left of 3 halves and slightly to the right, and look at the signs of those tangent lines. Now, we have to be careful, though. The point we pick slightly to the left of 3 halves can't be smaller than 1, because the interval that we're looking at is only from 1 to 3. So let's try this. Let's just use 1, because you know that's part of the interval. All right, so that means the slope to the left of this point is positive. Now let's move to the right, and let's try 2. And that means that to the right, we have a negative slope. So what that means is, because we're going from a positive slope to a 0 slope to a negative slope, that implies that this point is a maximum. In this case, a global maximum. Now, we haven't yet proven that yet. We can tell from looking at the graph, but if we didn't have the graph, in a case like this, we also have to test the two endpoints, just in the off chance that one of them is actually the maximum. All right, so again, if we don't have the graph, we can do this algebraically by testing the values of the function, or the slope rather, at those 2 points. All right, so this is done down here. All right, so, and I also reproduced the graph here so we can look at this more carefully. We know that here we have 3 halves. and 1/4. At the point 1 comma 0, the y value is less than 1/4. Here, we've already determined that this is 3 comma negative 2. All right, so the bottom line here is this. Within the interval, we can think of this point as the global maximum because it has the highest value of y, and this one can be thought of as a global minimum. And again, this is only because we're only considering the interval from 1 to 3. All right. Otherwise, we'd probably have something different. But if this is the only range that we're interested in, then, for example, if you're trying to maximize your profits within the interval 1 to 3, then we would go to this point 3/2. Or if we're trying to minimize your costs, then we would go with that point 3 comma negative 2. All right, so that was the end of 4A. And now we're going to look at 4B. So here we're going to introduce a couple more theorems, and then we'll get into something interesting. First of all, we're going to be looking at some applications here. So we're going to start with this idea of Raleigh's theorem. Now, we're going to start, now, by the way, the mean value theorem is the general version of Raleigh's theorem. We're going to start with the specific case, Raleigh's theorem. Then we'll work our way back to the more general case, which is the mean value theorem. So Raleigh's theorem basically says this, and it's very hard to visualize this without a graph. So this is what I've come up with. What they're saying to you is this. If f of a, for these 2 points A and B, if f of a equals f of b, then Raleigh's theorem says there's guaranteed to be a C in here somewhere such that that point represents a global maximum, a maximum or a minimum. Okay, it doesn't have to be global or local, but it is a maximum. In other words, the tangent is flat or it has a slope of 0. But only if f of a equals f of b. So, and you can see on the graph on the right, the f of a is not equal to f of b, so you can see there is no point where the slope of the curve is equal to 0. There could be one, but it's not guaranteed. So Raleigh's basically saying that if this case, or this is true, you're guaranteed to find a point in here somewhere, which is an extreme point. Now here's some more graphs in the book. You can see what they're, now by the way, this is interesting because you can see there could be more than one extrema within that interval. Okay. In all 3 cases, f of a equals f of b. And in the first 2 cases, there's one extremum, I should say. In this last case, there's 2. And there could be any number, but all Raleigh is saying is that there's at least one. All right, now let's apply this to a function x squared plus 2x. And first, we're going to prove that the theorem holds, and secondly, we're going to find the critical point. Now, the first thing we're going to do is get a graph of this from Symbolab. Okay, x squared plus x. And this is what it looks like. Oh, it's already here. Okay, good. So we're looking only at the interval from -2 to +0, or to 0, I should say. And so the important detail here is this: the function is x squared plus 2x. And the two endpoints, we're looking at -2 and 0. So in other words, we're only considering the interval from 2 to 0. F of A is equal to +4 minus 4 equals 0. F of B is 0 squared plus 2 times 0, which is 0. So F of A equals F of B. Means we know there has to be an extreme point in here somewhere. Now we have to find it. And so this is going to happen the same way it normally does. We'll take the first derivative, set it equal to 0. So using the power rule, we end up with f prime of x equals 2x minus 2. Set that equal to 0. Solve for x. And we're all set. X equals -1. So this is our critical value. And then we'd like to find the point, the entire point. So what we'll do is we'll find f of -1. -1. So in other words, the critical value is -1. This is the critical point. Okay, so we showed that on the graph. Oops, I labeled it incorrectly. Okay, so that's our extreme point, which could be a maximum or a minimum, although you can clearly see from the graph that it's a minimum. And in fact, over that interval, it is a global minimum. And we can find it out, prove that by either, we can look at the two the slopes on either side, or we'll see later on that we can use the so-called second derivative test. Okay, so that was Raleigh's theorem. Now, what about the mean value theorem? Well, the mean value theorem is a more general case. Raleigh's theorem is a special case where these two are equal to each other. So what is the mean value theorem telling us? Well, if the function is continuous over an interval AB, now what's interesting here is that it has to be differentiable over this entire, continuous over this entire interval. But it only has to be differentiable from A to B, not including A and B. So in other words, if you have some weird behavior exactly at A, but nowhere else, we're still good. Remember, we saw these graphs where when you have sharp points, the function is not differentiable, and yet it's still continuous. That's an unusual case. I mean, normally, if it's continuous, it's differentiable everywhere. But what we're saying here is that given these conditions, then there's going to be a point in there somewhere where the secant line between those 2 points will have a tangent line. Now we're going to need to look at a graph to see what this means, but the tangent line at that point is parallel to the secant line that connects the 2 points A and B. So what didn't, don't worry, it'll make sense when you see this graph. So here we are. So you get the two endpoints. This is the secant line between the 2 points. What he's saying is that in this case, there's actually two of them. We could find at least one point Well, the tangent line has the same slope as that secant line. Uh-huh. So that's what it's telling us. And they're also showing us then that here's the slope of the tangent line, secant line rather. Whatever the tangent line is, we're going to call that point C. Well, here's C1 and C2. These must be equal to each other then. In other words, that's the consequence of having the same slopes. The slope of the secant line on the left is equal to the slope of the tangent line on the right. Now, you notice that this is not necessarily a critical point. The slope of the tangent line isn't necessarily zero. But we do know that these two are equal to each other. This is the slope of the secant line, which connects A and B. And this is the slope of the corresponding tangent line. Okay. So here's an example, specific example. Y equals f of x equals the square root of x. Suppose we're considering the interval over 0 to 9. So the secant line has a slope it's f of b minus f of a over b minus a. Now this is the square root, so since a is 0 and b is 9, so the slope would be 9 minus 0. Oh no, I know what I did wrong. Sorry, this is not 3, it's 9. Right there, I goofed. Okay. And that's actually 1/3. So the slope of that tangent line between those 2 points is 1/3, which means that there's some tangent line over that interval that also has a slope of 1/3. The question is, where is that located? Well, let's find out. So the original function was f of x equals radical x, or x to the 1/2. Based on the power rule, f prime of x is 1/2 x to the minus 1/2, or 1/2 radical x. So what we need is to find the point x such that f prime of x is 1/3. Okay. So here's what we can do. There we go. Okay. So in other words, and here, by the way, here's the graph from the book, which shows us this. So here's 0, here's 9. Here's the tangent. Let me make this a little bigger so you can see it better. And it turns out that 3/2, or 9/4 rather, is here. So y would be 3/2. So this point is the tangent, which lines up with or is equal to the slope of the secant between those 2 points. All right, so now why does this matter? Because if we have a continuous function over an interval, and again, only differentiable over the open interval a to b, if f prime of x is positive for all x in that interval, then we know that this is an increasing function everywhere in that interval. If f prime of x is negative for all x in that interval, then it must be a decreasing function. Right now, it's like here, for example, if you look at this, any value of x that you choose between 0 and 9 is going to result in a positive value. So that means we're guaranteed that whatever the slope of this function looks like, it'll never have a negative slope. And then, and so once again, this is the result that we're looking at. If the derivative is positive for all x in that interval, then f of x is an increasing function over that interval. And if f of x is negative, then the opposite is true. So we're going to have an interesting graph here. It's going to show us 4 cases that we need to know. Upper left-hand corner, the function is increasing at an increasing rate, meaning that the derivative is positive throughout, but increasing. In other words, from here, if you notice, this is the tangent here, this is the tangent here. The slope is positive, but it's increasing. In other words, it's becoming more positive. Right? In the second case up here, both of these slopes are positive, but the first slope is greater than the second slope. Okay, so I'm going from left to right. The slopes are positive, but the second one is smaller than the first one. So we say that the function is increasing at a decreasing rate. The bottom left-hand corner, the slopes are both negative, but the first slope is less than the second slope. So the rate of decrease is actually increasing. In other words, it's like we're going down a hill that's getting progressively steeper. So this function is decreasing at an increasing rate. And then finally, in this last case, the curve is basically flattening out. It has a negative slope. The first slope is less negative than the second one. So here we're decreasing at a decreasing rate. Now, when we start looking at second derivatives, these graphs will be very helpful to visualize what's going on with second derivatives. But for now, we just need to consider the idea that there's 4 cases here, increasing at an increasing rate, increasing at a decreasing rate, decreasing at an increasing rate, and then finally decreasing at a decreasing rate. So we can combine all these now, make the following statements. A continuous function, f of x, reaches a maximum point at C, as you can see in this graph, if f of x switches from increasing to decreasing at point C. And conversely, at the bottom, you can see that a continuous function f of x reaches a minimum point c if f of x switches from decreasing to increasing. So here's what they're telling me. We can identify these extreme points with the first derivative, but we can't be sure that these are minima or maxima without more information. And this is that more information that we needed. And again, it's not the only way to do this, but it's one way by comparing the slopes on either side of that tangent. And this is all being justified by the mean value theorem. Now let's take a look at this. So look at this function. So we've got all these ranges where the derivatives are positive or negative, except there's three cases where the derivative is 0. And then we have that one case where the function is undefined. You can see it's got this strange behavior. This point, the sharp point, is an indication that the derivative is undefined. So these are our 4 critical points. And so we can conclude from this that we have a maximum, relative maximum, that is, or local maximum. Since we're considering the entire real number line, we have a relative maximum, another relative maximum, and B is a relative minimum. This one is neither, because if you notice, the slope is positive on either side. And that means that we don't have either a maximum or a minimum. Okay, in other words, in order for it to be a maximum or a minimum, the sign of the derivative has to change from either positive to negative or vice versa. If it's neither, then we do not have an extreme point. It's a critical point, but it's not an extreme point. So that's kind of a strange case, but that does happen. And so all of this is collectively known as the first derivative test. In other words, we're trying to find our extrema. Well, first, we already are able to find it by setting the first derivative equal to 0. But to determine if the points that we just discovered are maxima or minima or possibly neither, we're going to apply the so-called first derivative test. And it entails exactly what we've been doing. We're going to look at the sign of the first derivative on either side of our critical point and compare them to each other. Like here's a cubic function. This will be interesting. And this is what it looks like. You can see there's 3 critical points. And how do we find them? Well, we took the first derivative of this function and set it equal to 0. And since this is a quadratic equation, there will be 2 points where this is equal to 0. Oh, well, here we got a lucky break here. We can divide both sides by 3. And so this is what we're left with. Now, you can certainly factor this if you want, or you can use the quadratic formula. And what you discover is that x minus 3 times x plus 1 equals 0, which implies that either of these equals 0 by itself, or ultimately x equals 3 and x equals negative 1. We call these our critical values, or critical values. And so now we're going to need to test or apply the first derivative test over these 3 intervals. Okay, so in other words, since the critical values, again, were negative 1 and 3, we have to test the sign of f prime of x in each of these three intervals. That's what's going to tell us whether these are relative maxima or minima, or possibly absolute maxima or minima. Okay, so let's do it. So the derivative is right here. And again, these are the intervals. So that means you can pick any point in this interval. And so I've chosen -2. And you can see that ends up being 5, which is positive. Now, for the interval -1, 3, we can plug in, let's say, 0. And you find that it's negative. And then for 3 infinity, we can pick, let's say, 4. And that gives us a value of 5, which means then we have a positive first derivative. All right. So this is to summarize what we just did. So so we went from positive to negative to positive. I don't know if it's possible to sketch this graph just with this information, so I guess I won't. But we do have a graph of it. It's right here. You can see that here's our -1. Now, what I did was I plugged these critical values into the original function to come up with the critical points. So f of x, remember, is x squared minus 2x plus 3, minus 3. And so the two critical points were, critical values, I should say, -1 and +3. So f of -1 is -4. Wait a minute, is that right? No, it's not. Sorry. What did I do? It's 1 plus 2, 3. Oh, no, it's 0. Yeah, that's -1 squared is 1 plus 2 minus 3.